Welcome all of you for these interesting lectures. Here we will not talk about much about mathematics, talk about the art of river training work. It's a combination of science and art, and with the experience of hydraulic engineers, sediment specialists and the river engineers, they try to train the rivers for different purposes. So, looking that most of the experience in the United States of America, that is what I will share today, and some of the advanced country, how they have been managing the floods, and how they have been making the river is navigable, so that they can use as a inland waterways. So, the basic idea of that what the experience is there, and most probably I will following this book, the river engineering by M.S. Patterson's. That is the books we are following it, and partly we are following its river mechanics books. This is the engineering concepts, so mostly you know it when you construct any river training works. It is a combination of geotechnical engineering, combination of hydraulic engineers, and new constructions materials. So, it is not just a river engineering, it is a combination of geotechnical engineering, river specialist, and also the advanced techniques, geotechnical techniques what nowadays we have been using it. So, that is the reason it is a quite introductory levels, but there are many new things are coming it like geotextile materials and all, geotube and all the things what is coming up, but I will just highlight it. What is the experience of the rivers engineering works in the United States of America? Let me look at the next figures, which are very interesting figures, slides what showing to us. Before that, this is the content what I will talk about. Inland navigation projects in the United States of America, and we will talk about the lock and dams configurations what is there at the introductory levels. Then we will talk about dredgings, the floodways, even we will talk about the river closures. At the end we will have a case studies on Brahmaputra rivers, that is what the impact of the bridge constructions on fluvial morphology. That is the case study, that is what we will present at the last. Now, if you look at that point, if you look at this Ohio River navigations projects, which is way back in 1979 by the US Army Corps of Engineers. If you look at these rivers and you can look at this all these dam and locks. Okay. So, if you look at that from upstream to downstreams, how many series of the cascading dam and lock structures are there, and this is what the longitudinal profiles, distance versus elevations. Okay. And if you look at that, for each projects they have a like Montagone projects which are having the elevations 682, Mel Danny projects the elevations 485, and you have McAlpin project 420 meters elevations, and the Winan town is 342. So, if you look at this longitudinal profiles of the rivers and the intervention structures, you can see that more than 15 structures are there, which was constructed way back just after the World War I and World War II. This is the channels, is a 9 feet navigation channels, which is very famous for transporting the coals from the upstream to the downstream locations. And it has designed, it has been designed for fleet of the 10 barrages, and that period it used to carry about 60 million tons of the traffic. So, you can understand it after the World War I and World War II, these projects, the river navigation projects play a vital roles for economic growth in the United States of America, because they constructed a series of the dam structures, so that throughout the years they can have a 9 feet navigation channels. The depth of the feet will be 9 feet. Because of that, they construct a series of dam structures. If you can look at the series of dam structures, and that ponding elevations, you can see it. So, this is the way they make it the river is a navigable, and throughout the rivers, throughout the seasons, they have a 9 feet navigation channel flow or the river flow more than that. So, that is what they have designed it, and that is what it took it almost 30 to 40 years to construct all these major structures, makes this river is river was navigable, and it has been a navigable rivers. That is what, if you see, that is the major interventions what is done in Oyo river navigations projects. Similar way, if you look at this Arkansas river navigation project, which is part of USA, is part of the Mississippi river basins, and if you look at the reservoirs, you can see that series of the reservoirs. Okay, all are the cascading reservoirs and the dam and the locks. Okay. So, all these are cascading reservoirs and all. Again, if I plot the longitudinal profiles, here the unit in some miles, and we have the elevations, and you can see this the dam structures. Each dam structures having a numbers, and each number having this lock and dam positions. Okay. So, they have the ponding, and they also have a keeping these waters, ponding waters at the different levels, and the lock and dam structure. So, that any navigations can flow smoothly from upstream to downstream, and it can carry the significant amount of the it can transport the significant amount of the upstream coal or other materials. So, they make this river is navigables, and based on this a cascading the dam and lock structures, and that is what is you can see it, and that is what it made them to make it one of the successful projects to connecting the rivers. No doubt there are the advantage and disadvantages, like it has certainly helped the flood protections, the bank erosions, but the sedimentations was the bigger issue, but that is what is the strategy how to maintain sedimentations, the cascading sedimentations, because of the series of the cascade dams. Those are the issues. Still many of the engineers, hydraulic engineers are trying to find out the solutions, how to optimally use the cascading dams project, so that you can reduce the sedimentations. But no doubt this type of extensive river training works for navigable the channels, navigable for making the navigable channels, so that there will be a two-way traffic movement of these vessels can be done it. That is what this thing, and many of the text is very clearly said that because of these are the projects was the after the World War II gives us a boom to the economy of the United States of America. So, that is the point what we to know it. The same way, if you look at that, that means what is the locks and dams? You can understand it is a locks and dams. So, basically it is required to dams, you know it is required to sustain a educated the navigation depth. That is what is 9 feet, okay, 9 feet depth of the water minimum, that should be there. And the locks is to allow the ships to navigate in a rivers stiffened by artificial cutoffs. So, if you look at these figures, okay, this is the part of the rivers, this is the left bank, this is the right bank, and you can see these are the spillway gates and the stealing basins, okay, and there are the gate piers are there. And if you take the cross sections, you can see with a gate, upper pole, lower pole, and the stealing basins with the baffles will be there, spillways crest, and the river bed. So, if you look at that, so more detail we are not going it, mostly you can get in hydraulic engineering, how to design all the aspects, how to design the spill gate, how to design the stealing basins, the gate piers and spillway gates. That is not we are discussing here, but that is the arrangement for a barrage or the dams to flow through that. But to passing through the ship, okay, we need to have a locks arrangement. So, if you can see there is a lock arrangement, this is the lock chain, this is the upper gate, this is the lower gate, this is a lower lock approach, this is the lower guard well and upper guard well. So, ships comes from this, goes to this lock chambers, then goes through this. So, this is the arrangement. Many of the things there will be the one side is the dam, another side will be the lock arrangement, which facilitates a ship to pass through those ones within having the upper and lower with a storage and the lower lock approach. We will talk more details in the next slides. So, if you look at that, must be spared to maintain the navigation depth throughout the poles. Okay. And the river navigation project, lock is generally located near the bank at one end, that is what is you can see the trick to minimize the adverse effect of the spillway discharge on traffic. Okay. So, that is the basic ideas, and you can just see that the lock and dam basic features, okay, which may vary from location to locations. It may vary the design of the spillway, sealing basins and all. The most difficult things of lock and dam arrangement will have a locks, with you have a upper lock approach, lock chambers, lower lock approach, and their upper guard wall, and you have a lower gate, you will have a lower guard walls, which is facilitates the ships to go through these lock arrangements, and the gate, spillway gate and the piers to maintain this the pole depth. That's the idea, to maintain the pole depth. That's what's necessary to have the gate, and you have the also the lock. So, this is the typical arrangement, but it varies from depending upon the geology, depending upon the site locations, depending upon economy, and we try to make it differently, but typical structures like this will have the arrangement for the spillway and the gate arrangements for storing and having the pole of water depth, and there will be facility of the lock, which facilitates the ships can pass through these ones. Now, if you look at next part, you can see that's lock arrangements. You can see this upper lock and the lower locks, you can see it, and it facilitates this is the lock arrangements, it opens and closes, and that is the reasons the locks is educated depth for the navigations, gain access to the lower or the higher water levels on either side of the dam. It's have a open chambers, it has a gate at the upper to fill the waters, and you have a lower pool which is discharge the waters. So, that is what we do it. It's a costly, it's expensive, and it's depend upon how much time it take to fill the chambers, the larger filling times, emptying times. That's what also matters, how locking times we do it when the ships goes through these lock systems. Now, if you look at very interesting figures, which is given through the P. Julien book on river engineering and the chapters, which is a river mechanics book. So, if you look at that, if you can try to understand these figures, very interesting figures which is showing it how do we have a arrangement for a lock systems. There will be upper pole, there will be the lower pole, and you have the lock chambers. Okay. So, that is and you have upper gate and the lower gate. For to do this filling, this is the filling valve. So, if you look at the water can come from upper pole, can get into the from the lock floor, it can get into this lock chambers. Then you will have the lower poles, okay, and you have the lift, okay, lower gate steel, okay, you have the lower gate steels. Now, if you see that FC entered, the ship enters to the pole, that is time we upper gate is open, and that is what it enters into that, and that time it has the closed here, and the ship enters to the chambers, so the lower chambers, as soon as also the water is extracted from this, so that it can goes below down, okay, to the levels of the lower pool. That is what its arrangements. Again the water goes out from this and the ships goes down. As it goes down, it comes to closer to the same level of the lower pool. At that time, we close this gate, open this gate. Okay, that is what initially close it, still go to that regions, then we open the gate and the ship pass through it. Then you have these things. It is very mechanical way of arrangements, but you know it needs to design all the structures like gate, these filling valve arrangements with a filling chambers, all it depends upon how much time it takes to filling the chambers or emptying the chambers, and based on that we design these lock chambers, upper pole and lower pole, and also filling valve and emptying valves. So, these are very typical figures and quite interestingly it is indicating for us the how a lock arrangement is there for the navigation purpose. That is what is showing that. So, that is what is here, the same things is telling it here, that locks admits the water to fill the chambers from the upper and discharge to the lower pool to empty the legs, lock. Okay. The upper lock gates are the open for the two to move into the lock chambers. The upper lock gates and filling valves are then closed. Okay, you can understand it is okay. The emptying valves are open to bring the water surface in the lock down to the level of the lower pool. It's the same things what I discuss it, and the lower lock gates are then open, then two moves out of the lock chambers into the lower pool. So, this is a very nice arrangement how to a ship goes from upper pool to lower pool through a navigational lock. That is the very interesting things is there, and we have a navigational lock arrangement, typical navigational lock arrangement. More details you can see its figures, it is a quite you can get it nowadays. You have a Google images are there, you can see this the gate, okay, so and you can see this how the ship is passing through it and how these gate openings are happening it, all you can understand it nowadays. You all have a the Google is a source of information nowadays. You can get all the source of information how the lock and gate and how the civil engineering structures are there for dams and the locks arrangements. It is not that difficult. Now, if you look at that way, the next part is nowadays we have been advocating that dredging a river, okay, dredging a pond. What is that? How much cost effective it is? Those things I am not going details, but very introductory levels I will talk about the drainage towards the river management. So, if you look at that, so often we have the sedimentations of the rivers, okay. That because of natural sedimentations of river, the river aggradations happens it, the river becomes more shallower and shallower, or we confine the rivers. As we confine the river, the more the sedimentations happens in aggradations happens. So, because of the aggradations happens it, river flow carrying capacity decreases. So, flow carrying capacity decreases. Okay. So, that is what it happens it because of embankments, because of confining the rivers, because of having the levees we also confine the rivers. Because of that there will be the sedimentations, okay. There will be the sedimentations. So, if you do not remove that sedimentations, no doubt the carrying capacity of a river decreases with the time. So, decreases with that, and that may be slowly it will have the dangers to the embankment or the flood protection structures what we have. So, the basic idea is that to dredge that materials means remove that digging and remove this river bed or widening the river. So, we can increase the width of the river or increase the depth of the rivers. That is what we call it deepening or widening the navigation channels or the river channels. Okay. So, that to have more carrying capacity. So, basic idea is to increasing more carrying capacities of the river. So, that it will work. So, the equipment generally we use either the dredgers are defined as a mechanical times or the dredgers are generally two types, one is mechanical type, other is hydraulic types. In mechanical dredgers we have bed materials which is have a dipper or bucket to this thing. I will show the figures for that. The hydraulic dredgers is a pick up the dredge materials by means of suction pipes and the pumps. Okay. When you talk about hydraulic dredgers, that means it is just pump the bed materials, okay, and it have a suction pipe and it have the pumps and it has a disposal part. But in a case of mechanical dredgers, it is a dipper and it have a bucket. That is what it helps us to dig the materials and remove this material from the bed. Now, if you look at that deeper dredges, if you look at this dredges part, there is fixed it here and there is a toughing, the buckets are there and deeper arms are there and drag host is there. Just it is dipping that things, okay. With the buckets we are just removing it, we can just understand it way we dig a soils, okay, dig soils, okay. That's the concept, we follow it and this is what the river bed. So, we can have a deeper arm, you can have buckets, you can have a dig the soils and as you dig the soils then you can take it, okay. And to make it stable, so you can put this main spot, so fix this dredgers and take these bed materials from that place, okay. That is what we do it. Basically excited hard compacted materials, blasted rocks, we can all do it. Nowadays technologies are there, or the dredgers having very high end dredgers are there, we can actually dredge the rivers with having this part. It can operate very little guiding space and accurately control the near the bridge locations like the structures, okay. You can accurately dredge the a critical locations like a bridge locations, you have a bridge piers, you have a bridge abutment, those are the critical structures. We can use this type of structures to dredge the materials. Now, if you look at the bucket dredgers, so which is you can see it's the bucket concept is there and that the bucket chain is there, the ladder is there and buckets are moving like this and there are the ladder fibers and the dumping of these materials and you have this ladder hosting wire, side wires and the head wires. So, if you look at that, these are all mechanical components what I am talking about, and as a river engineers we try to know it how much of dredging can happen it because of these bucket dredgers. So, basically the bucket dredges use the interchangeable buckets, okay, that is what you can see, the chain of the buckets are there and different operational purpose you can have a different type of buckets, okay. An open bucket can have a 9 meter cube for volume of the bed materials, then close to the raised and emptied. So, because then it is closed then empty up. So, that is the process goes on, okay. So, it is a very interesting. So, we have the dredgers with a buckets which can have a dredge the bed materials as a buckets and try to store it here, okay, store it here. So, that is same way if you talk about the hopper dredges, which is basically it is a self propelled sea going vessels maintenance dredging. So, we are progressive deepening by successive pass, okay. So, most of the times what we do it dredging is a progressive deepening, it is not like in a one day we do it, okay. That is the idea of a river engineering, it is not that do a deepening in a one time, okay. You do a progressive deepening, you can understand it how the river responses are happening it. Otherwise, the dredging of the channels, dredging of a sea fronts does not make the sense. That is the reasons we do progressive deepening, okay. Or we do a maintenance dredgings. We do the dredgings just to maintaining the 9 feet depth or maintaining the draft requirements. We do not go for high level of dredging things. So, it collects the connected materials in through the channel bottom through a suction pipe stored in the hoppers. Okay, that is what is there. This is the suction pipe and it also stores in the hoppers. The dredges are emptied by opening these bottom doors, dumping of this entire contents of the few seconds. Okay. It takes the dredging materials and then dumps it and come back it. That is what the hopper dredges. Okay. Hopper dredges is there and you can see that dredged part and taking these materials and filling the dredged materials and dumped the dredging materials after where we have to dispose the dredging materials. That is what we look at. Same way if you look at that dust pan dredge, okay, very interesting part. You can see this dredger is just like a dust pan. Okay, you can see in any house how you remove the dust. Okay, we use the dust pan. The exactly same concept. We have the dust pan dredge. The basic idea is that is a pressure water jet that loosens the bottom materials. Wide flare flat suction lines intake for sedimentary walls. Okay, that is a two components. First component is having the pressure water jets which loosens the bottom materials, the bed materials. The second one is that it has a flat suction line intakes. Okay, that is what is that, the flat suction line intakes. Okay. So, that is the take the sedimentary from that is normally discharged into the open water through a relatively short pipeline up to 30 meter long or a longer dispersal line requires a boosting pumps. So, you can dump it within a 30 meters or if you do not want to deposit do the disposals within the 30 meters, you can have a booster pump. Okay. So, because it is a mix of the sediment and the waters, you can use a booster pump to dispose at a far a distance or a locations where you want to do the disposals. So, if you look at this dust pan dredge, very interesting dredge part. Okay, it's have a that it has a two component. One is a pressure water jets that loosens the bottoms. Then we have a wide flat flared and flat suction intakes, and you need to have a booster pump if you want to take the dredge materials beyond the 30 meters. You can have the booster pumps. Okay. More mechanical designs and all the things we are not going here, but these are things we can use it like a alluvial rivers where you have the very loose sand and the silt materials or the clay materials which we can loosen with help of pressure water jets. Then we can suction line take the sediment from that and you can dispose it because you have a booster pump on that. These are things we can do it and which is necessary now when we talk about making national waterways of our country to navigables. Maybe the dredger can be used for some of the stretchers to do a maintenance dredgings. Let I show the figures how we have a same way you have the cutter head dredge. Okay. So, that is a suction pipe, cutter head and you have the dredging. So, it is a cutting. Okay. That is the reasons he is the most efficient. What I tell is having a rotating cutter around the suction pipe intakes. Okay. It is cutting the thing and it has dig and pump the alluvial materials including the compacted clay and the hard pans. Okay. So, because it have a cutting tools. Okay. That means is a cutter head is there. That is what into like you have the very hard pen, the clay materials are there, that is what you want to remove it. You can use these things because it has a rotating cutter okay, around the suction pipe intakes and that is what it helps to do, remove these compacted layers and the hard pen formation. Generally it have a cutter head baskets, ladders, suction line, A frame, H frame, pumps, gantry, sports and the pipelines up to 90 centimeter diameters. Okay, pipelines can have. So, if you look at this, the basic structures what is there in this sea. So, nowadays these technologies are there. Many of our country maintaining national waterways, we have been also using maintenance dredgings. Let I put it how a river like Arkansas rivers, we have been using different strategies to make the river navigable. It is not a only solutions of the dredging the rivers. If you look at this rivers, very interesting river which is 1972 way back in United States of America, how they do the maintenance dredgings, how they have the river training works. So, if you look at the levee structures, you can see that they are very far away, there is a levee structures, that is what is to protect the floodplain, and they have given enough river space. Okay, that is not the levee is just parallel to the rivers, that is not the concept. You see that levees were constructed so far away, river has a one space. Like for example, these is the positions they have given enough space that cut off rivers which are morphologically cut off happen it, and they put the cut off things are here. So, if you try to understand it, the first they have given enough space to the rivers, confine the river through the left levee and the right levee, and that is what is designing it. If you look at that, and within that they try to look at all these geomorphological variability in terms of river cutoffs, meanders, the history of the rivers tell about, the morphology of the river tells about what was the space of the rivers. That is not a big issue. We can use a series of satellite data, we can find out the river space, and we can design what could be the space, what will be the layout for the levee. Okay. The second part is that if you look at, there is a lock and dam structures here. There are the series of the spar things are there. See, there are the series of the trawl and there are series of the spar structures are there to confine the river or divert the river from that. Not only that, there is a trench field revetment. Okay, so, again I am talking about it is a trench field revetment. There is a trench, in that they have filled the revetment, that is what is there, the trench field revetment. See, this is well designed, the trench field revetments are there. After doing so much things, okay, having the levee, the spar, the pile structures or all sort of spar structures, still they need to find out the depth, they want to have a major dredges. So, this is the dredges materials. Okay. So, it is not only the dredging is a solution for that. They construct, they confine the rivers, they want to have a stage wise confinements, like the levee is a higher discharge confinement, then within the inline structures are there which is confining it. With having this protective like a trench field revetment, we have all spar structures, still it is not possible to get the 9 meter depth of water. That is the reasons they maintain the dredgings, this is the maintenance dredging. That is a combination of all these river training works have been followed by the United States of America to maintain this river navigable. It is not that easy, that is what the point and to highlight it, and that is what is happening, this how these structures are there, how they construct the cutoff, they construct the levee, they construct all the river training work, the trench field revetment, and also where they need a major dredge to work. So, the dredging are the minima, at the last option is there to dredge the river, and that is what they try to look at, where they can do it, where they cannot get the 9 feet depth of water for river navigations. That is my idea to convey you. Let us come to talk about the floodways. Okay. Many of the times you know it that we have the discharge is much higher order when you talk about 10-year plot, 100-year plot. And when you talk about the plot, we should not talk about only the peak discharge. Okay, we can talk about peak discharge. Also, we should talk about the plot volume. How much of plot volume is coming? How much volume of water is coming for that specific plot of 100 years, 10 years, or 5 years? So, if you can try to understand it, then naturally the river has one space, it has one plot plane. But with the times, we have encroached the part of the plot planes. So, we have constructed the embankment, we have constructed a series of the dam structures, like for example, of Hirakud Dam projects, okay, which is one of the largest dam, early 70s, 50s, 1950s and 60s, and these dam structures storage enough water so that storage can reduce the flood peak and the flood volume, the downstreams of these dam projects. That is what is the strategy was there, but there are new strategies coming, is that you can have a flood storage, you can have a very low lying area, you can store the waters, and many of the time they call it flood wedge or the flood divergence, or the many of in Germany they talk about flood folders. So, basically the low lying areas which are designed to store the excess flood waters, a return period of 10 years, 100 years or 2-year return period flood. So, nearby the area, the depressions area near the rivers where you can store enough waters. That is one reason you can have a series of the wetlands, and you can design the wetlands such a way that they can store the flood waters during the 2 years or 10 years or 100-year floods. That is what the idea is to come it, and that is what it to design it, the things. So, there should be outlet, the spillway, and we should have a control devices. Okay. So, to manage this we should have a control devices. Okay. So, you can have a control of gate arrangement and all. Synchronously you have to manage the floods, so that you can store the waters in a low depressions area, man-made reservoirs, or you can store the flood wave waters in a less vulnerable part of the things. That is what we stretch it. Basically, it is emergencies for the high flood, it contains high proportion of sediment load, but you should know it when you do the flood managements. There are also the huge sediment loads. How do you manage that sediment load? And that is what, as a river engineers, we should look at. We can store the waters for the time being during the flood periods, then again release it. But what happened to the sediments? Whether that what is going to deposit, and as it deposits, is it has advantage for agriculture or not? Those cost benefit analysis needs to be done it to look at the flood storage during the extreme flood, like a 2 years, 10-year, 100-year floods, and that is where to be manage it to have a different type of storage mechanisms. Now, if you look at this is what earlier concept of the river corridors. Okay, it's what I discussed in the last class. I am not going this, but if you look at man channel, you have a lot of things. Okay, it's a river. It's nowadays it's man-made canals. Okay, it's a river which is supporting the ecology. It's supporting the flood plain, it is supporting these islands, it is for having the left bank, right bank, all you can see that flood plain forest, and you can have all these ecologies, life cycles are there. But let us talk about that, what we try to do it. That basically we try to have channel conferences. That means we need to know, increase the flood carrying, the river carrying discharge. That is what is our idea. So, you need to increase the river carrying capacity. How you to do it? You just look at the very simple is that Q equal to A into V. V is equal to 1 by n r to the power 2 by 3 s naught half. Okay. I am using the uniform flow concepts. This is the Manning's equations. See, I can increase the discharge of the rivers, either have to increase the flow area or increase the velocity. To increase the velocity, I have to reduce the n value. We should reduce the n value, increase the s naught value. That is a very simple thing. With the two simple equations of Manning's equations, and the flow rate is equal to area into discharge. If you want to increase the discharge in a river, that means I either have to increase the flow area, reduce the n value, so that the velocity will be more, or have to increase the bed slope. That is the three concepts where we can use it to increase the carrying capacity of the river. That is very simple things. Reduce the roughness of the bed materials, that is what is we look it to reduce the n value. You want to try to remove these natural vegetations, but you try to know it the river has the ecology. That is you try to look it how much of ecologic aspect of the river we are losing it, that should be quantified. We can increase the cross section of the river, that is what is very easy, that as you increase the cross section of the river, you can stiffening the increasing the channel slope, we can do it. Okay. Or you can have a clearing the bed and plot plane from these vegetations, that means you want to decrease the n value. So, all what we are talking about, all with respect to these n values, and that is, and remove the sandbar the islands, that is what is you can increase the, both you can do it, increase the flow area as well as you are decreasing the Manning's roughness coefficients, that is what you do it. Smoothing the bank with a revetment, that means again you are talking about that, make it the river bank resistance is as close, becomes a 0. So, n value you want to reduce it. So, by putting the bank materials with a revetments, but when you do these type of things, you try to look at what is the ecological disturbance we are doing it. That the part we always should look at, because that is the part we have to debate it in terms of ecological benefit or ecological loss what we are doing it as we are increasing the carrying capacity of rivers. That is very basic things what you can understand it. Now, if you look at that or you can have a dredging the channels, we already discussed it that we can have a dredge the channels. As you see in these figures, we have the dredging the channels, and these two figures are showing it how the sedimentations happens it, okay. How the sedimentations happens during the flood. So, there are the lot of sediments goes it, and that can have a deposition of the sediments at this point, as you have a, that is what is the point, we have a natural levee. You have a natural levee formations because of sedimentations of this, okay. And as this flood after the stream flood, again the silting off happens it. This is cyclic process happening. Please try to understand it. The river have a episodic events like a 10 years, 20 years events. It does a episodic depositions and the erosions. That's you try to understand it when you talk about river depositions and all. So, that is the idea you have to look at, and as already I discussed about the cut-off channels, river meanders it and have the river cut-off channels. Now, if you look at that, when you have embankments, you people have known the earthen embankments or the levee, many parallel to our the river systems. If you talk about in coastal part of peninsular regions, you talk about Ganges river, you talk about Damodar rivers, we have a series of embankments which we many of the times we do not feel that is embankment, because we have been a dual proposed embankment, the embankment come roads or embankment come the highways. So, for example, if you look at the Ganga rivers, we have the two national highways are confining it, the Ganga rivers from starting from Bhagalpur to Patna. So, this what we consider is a national highways, but it is an embankment of the Ganga rivers, the confining in the left bank and the right banks with a different national highways. So, if you look at that way, we have the structures in our country, there are a lot of embankments are there, and you have a how to make an earthen embankment, how to design the embankment levels, and what type of bricks we can take it as embankments, which partly discussed in hydrology courses, we are not talking about here. So, but nowadays people talk about flood walls. Okay. You can see the Tokyo cities, okay. There are the structures, okay. The similar way can look at this the left bank and right bank of the Sabarmati rivers with a riverfront developments. You can see these are the roads, it's are the flood wall, okay. It is not the roads, and if you look at these structures and you can try to understand it, what is the height of this flood wall, okay. It's a flood wall which is a concrete structure similar to the levee, and that is what is mostly found in urban areas, and its levee reduces storage capacity of the river, and the floodplain restricted the flow in the conveyance. The reduction will be higher water levels, limited flood wave attenuations. That is what you can understand it. As we put the flood walls, what is going to happen is we reduce the width of the rivers. As we reduce the width of the river, restricted the conveyance, that will induce the higher water levels, and the higher water levels and the flood wave attenuations behavior will change it. That is, as a river engineer, we try to know it, what will be the effectiveness or performance when you design a flood walls. Okay. That is, we do a hydraulic design of the flood walls. Mostly we follow in urban areas where we can afford to have the flood walls. Okay. Now, if you look at that is the flood walls, which is given 1978 by US Army Corps of Engineers. There is a reinforced concrete flood walls. See, if you look at, there is a river side, this is the landslide, you have the flood walls, which is a 16 feet height, okay, 16 feet, okay, you can understand it, okay. These are concrete structures, and it have the shape like this to stability of this part and create the flood wall like these structures, okay. The same way they have the where this space of the flow line is not available, they can have the revetment. Then there is a area which can be used during the non-flood periods. Then you can have the revetment, again the same 16 feet, 8 feet and 1 feet the flood walls, and then you will have a partially levee and you have a natural grounds. So, if you look at that, the way back we had a concept of the flood walls. Okay. If you look at we have a major cities nowadays, we have think about the flood wave concepts, which it's expensive, but it's a long durations, and we can protect wells because we have the flood wall having this stone revetment, having a 16 feet flood wall, and that is what is designing of the flood wall such a way that it can sustain the water pressures, and you can have a protect the natural ground or the landslide sorry. Now, if you look at the basically if you look at that levee designs, I am not going more details because that is what is in generally discussed in geotechnical engineering, how to design an embankment. It's like you have to have a seepage control devices, you should have there should not be overtopping of these embankments, you should have a proper freeboard for that. All the things are there. When you talk about embankment, designing of embankment, that is what is there in part of geotechnical, and this. So, basically you should talk about the embankment breaching because of seepage and the piping or overtoppings, and when you have a talk about coastal areas, you can talk about the tides and this, and the stage we define it the design plot along with the allowance for the pre-boards. That is what we did, and you should anticipate it whenever you have these embankments, river is going to stage of aggradations, that depositions, sedimentations will be, depositions will happen, that aggradations of river happen, that is anticipated. That is the way that strategically you have to look at that how to confine the rivers as well as should not have a or should have a minimum aggradations, or you have to look at how to manage these aggradations because of embankment based confining the river space. That is the idea you should think it, and if you look at the flood walls, okay, it is very nice structures. Okay. This is the river side, this is the landslide, so you can see the structures and you can see this revetment, you can see this road inside the rivers which can be used during the null flood periods, and you can make it a river is a riverfront development, or you can make it river is a place where you can really enjoy our life with have a all these facilities with a flood wall, riverside space, and we have the protections work under this. That is the way it's been managed that, and this is okay in naturals, you know it that crown width should have the width of for the traffics, whether you want to design for one way road traffic or two way road traffics, you can use the width for that, but this is what river conditions that. So we can make it river is beautiful when you make a proper riverfront development. That is the things wanted to convey it. So we can have a protect the river as well as we can make this place will be a one of recreational facility of this river with, as you have seen these photographs, we can make it the river is front development as river is friend to us, it is not reversely. Okay. So, that is now if you look at very interesting part as you look at seepage in the levee. I am not going more details, you can talk about, you just can refer to any geotechnical books how the levee should design it to reduce as much as seepage problems, but you can have the seepage effect like the, for example, here it is a sand boilings happening it, and you have to have a protect 2 trenches, pressure relief walls, cut off trenches, seat piling, impermeable blanket, landslide seepage bombs, all the things are there in geotechnicals. You can design to reduce these sand boils or the failure of levee to have a protections for the seepage. That is we can you look at more details here, and I am not going much detail how to make these things. If you look about control of the floods at the tributary level or the main rivers, it is a compositions of different strategies to be followed it. It is not a one way things like, for examples, you can talk about the levee structures, you can have a culvert and with the flood gates to control it. So, we can have a control flow mechanisms with a culvert and the gates. You can have some locations where the gravity flow cannot occur during the extreme flood event, the flow congestions happens it. Those are the reasons we can have a pumping plant. So, if you look at that, there is a series of flow control devices with a culvert and flood gates, embankment, pumping plants. It's not a one way solutions, and these are the strategies nowadays has been following it. The urban areas where we know it, there are a lot of floodings happens it. We have the culvert with the gates and the pumping arrangements, and we prepare the drainage like this. So, the basic idea is that, and to say it, it is urban floodings and all the things we try to look it this way. If you look at this, you can have water pumping, or also you can have a river culvert with a gate arrangements. These culverts can be designed it depending upon the stream flood scenario. What would be the scenario? And these are things nowadays available in a Hackeres river model with different structures, inline structures, the side structures, all these combinations you can look at. What could be the level of this, the gate structure, what could be the pumping, at what time we should take it, all the scenario we can generate it and can be used as a design for the gate arrangements of, or the culvert arrangement, pumping capacity, all we can do nowadays with a tool of Hackeres river models, with having a different structure combinations of inline structures and the side structure. We can implement it, and you can look it during the extreme flood events, during these normal flood events, how do we manage all these infrastructures like pumping infrastructures, the controlling infrastructures, and those things are possible if you have a properly designed these drainage structures, also the control structures, that you have to have an idea. And nowadays we have all the tools are available, but we have the data. You have to try to look at that how we can make it a very effective flood management with a combinations of all flood control, flood storage, and the pumping facilities. That what can be simultaneously use it for effectiveness of the floods in a river or in an urban area. Some of times we go for the river dam closures. Okay, that's very simple things. We close the rivers like a penny rivers. How do we close it to have a structures? If you can look it, construction beside the rivers, completely closures, flow diversions, partial closures, flow contractions. So we go stepwise, stage wise we go it to close the rivers. Okay, construct the dams. So you first construct the dam beside the rivers. Okay, then you complete the closures and flow divert it, and partial closure and flow contractions. All we do it. So it's a stage wide dam constructions. What we do it things, and here I am showing it very simple thing. The dam constructions beside a rivers. Okay, so you can see that it started dry constructions area, where you in a dry area we are constructing the lake, we are constructing the dam, and later on we put the dikes and divert the rivers. Okay, and that's what these are the cut-off channels. So we make in a dry area the lock arrangements, the dam, and later on we just put the rebatement of the rivers and close this band and make it this channel. So that's the reasons we go for step by steps the constructions beside the rivers, what we get it, and it all depends upon what geology is there, what is the morphology of the rivers, what type of stepwise constructions we should do it. Next, if you look at that partially closure, we do it with a coffer dams, and that what the partial closures of the flow contractions we do it with a coffer dams. If you look at the structures of the coffer dams and filling these materials, that's what is showing that how we can design it, the backwater report, properties damage, and the scour all. So we can do a flow contractions with the coffer dams. These are temporary structures. We construct it, and you can see that the temporary constructions part, which is having the cellular cells like the things or diaphragm cells. That's what is provided, and it has a one advantage and disadvantage to make a coffer dam cells, and that's what we call. Then you fill the materials. That's what we do it. I close these lectures with showing this the performance of river Jamuna bridge, river training works. If you can look at Jamuna bridge locations, which is one of the largest bridges on the Brahmaputra rivers in Bangladesh. There was a lot of problems with that. It had a scour hole almost 45 meters below the average flood levels. It's one of the highest scour holes you can say in that, and it has make it because of shifting of the river considerably, it's very difficult to have a protect the slopes, and that's what they are doing with a geotechnical, and they try to make it river these bridge constructions, and they try to look at what the morphology effect is there. That's what is the papers in river flow 2012. If you look at this part, you can see that one of the cases the river has changed the course, and it has changes the flow separations, vortex sheet, scour hole and eddies. Because of that, there is damaged sections. You can see that the guide bond, the damage is there, and that's what it happens the flow behaviors during these a particular floods, where is the guide bond outflanking happened and possible the flow patterns. Very interesting if you look at the next figures. Looking this figure, you can understand it. Okay, that this is the map of channel incidence map of 1985 to 1996. It is showing it the same locations. That cut the points is a more the chance to river is there. This is the before construction, this is before constructions, this is the after construction of this bridge. Okay. And you can see how the morphology of the rivers of the downstream has changed it also changing the upstreams. Okay. So, you just look at that within the 20 years, by just constructing a bridge with a confining the flow depth with a guide band and all, there are extreme conditions are there are the chance of the failure of guide bond, but the long terms the morphology of the rivers, which is much broader here, it's the breeding patterns has reduced here in downstream, as well it is affecting the breeding patterns in the upstreams. The river has a response, and that what is makes us try to understand it, how it happens. It takes longer time, like if you say that's almost 10 to 12 years, it is responding the river because of this confinement in terms of reducing this channel morphology. So, with this let me complete today's lectures and with thanking my student groups, but let have the quote, the study of the mathematics like the Nile river begins in minuteness, ends in the significance. That is what hold good for river engineering. Thank you all for this lecture.